All right. I'm going to start my talk with a very recent interaction that I had with AI. I asked an agent to implement a very simple application, a drag and drop list. To my surprise, AI answered with a very simple question: how many items will my list have? This very simple question hides one of the toughest problems in software engineering: reordering items. Let's look at the real-world example. Imagine that you are in a library full of books. Each book has a label, a number. All the books are sorted, so you have book 1, book 2, book 3, all the way to the end. A new book arrives, and you want to insert it in the first position. So you grab the new book, and you insert it in the first position. But now, 2 books have the exact same label. How do we fix this? We have to relabel all the books from the beginning to the end. So your book number 1 becomes 2, your book number 2 becomes 3, all the way to the end. What if we move a book from one position to the other? Let's look at the following example. I have 5 books, and I want to move my book number 2 to position 4. But now, I have the exact same problem. All the books between 2 and 4 have the wrong label. The fix is the same as inserting. We need to relabel the books between 2 and 4. I'm Ignacio. I'm a staff engineer at Shopify, and this exact and very simple problem was causing headaches in one of the largest Rails applications in the world. I'm very proud to be here and share with all of you a project that I founded and led, and many engineers contributed with several optimizations that I want to share with all of you. Before diving in, I want to say thank you to the organizers for bringing all of us here together in Brazil, São Paulo. Thank you. All right, let's dive in. For this, I'm going to use an e-commerce example. In e-commerce, there are 2 key concepts that we daily use. First, a product. All of you know what a product is. It has a title, description, a price, and other metadata. And then we have collections. Collections allow users to group all the products together, give it a name, an image, a description, and other metadata. Think about your newest products collections. The World Cup 2026 collection with all the jerseys from the national teams. Collections has a key feature of drag and drop the product. So I have my list of products, and I can grab a product from the top, move it to the bottom, the middle, or grab a bunch of products and move it to a specific position. Let's look at some code. For this, I'm going to assume that we are using a relational database. Let us start with our product table. It has an ID, a title, a price, and other metadata. A collections table, title and ID, and other metadata too. And then we need the join table, the one that references the product and the collection with a foreign key. Let's implement the models in the active record layer. We will start with the product and the collections active record model. The intermediate table that has a belongs to the product, it belongs to the collection. This is a classic many-to-many relationship. So let's add the relations in the product that has many collections through the intermediate table, and a collection has many products through the intermediate table. But remember, I mentioned that collection also implements drag and drop list, and this is not implemented here. But there is an obvious solution to this problem. We can add a position. We can add an integer there in the join table, 1, 2, 3, all the way to the end. This is the exact same case as the books that I mentioned before. This is very simple, right? This pattern is everywhere. It's in your e-commerce shopping list. It's in your music playlist. It's in your Kanban board that we daily use to track issues or features. And it works fantastically well, we see it, until it breaks at scale. Let's do some napkin math together. For this, I'm going to use the worst case scenario. Remember, I have a list of books. I insert at the beginning. I need to relabel all the books to the end. If I have a list of 1,000 items and I insert at the beginning, I'm going to be doing 1,000 writes to a database. Of course, engineers are smart, databases are smart, and instead of firing 1,000 round trips to the database, we do a single or a few round trips, and we batch them all the queries together. But still, this is 1,000 rows that we write just to insert a single item. What if we have a medium list, 25,000 items? One insert, that's up to 25,000 rows that we write. And we can generalize this concept. N items, one write, one insert, that's up to N writes. And this is ON. And sometimes ON at scale is a killer. Let's go back to the original example of our library. Imagine that many librarians reordering books every day, every hour, every minute. This is not a theoretical problem. This is something that is happening in production right now. Okay. I think we have a very good understanding of the problem now. Let's pretend that we need to ship a drag-and-drop list to production. We all together are going to work on a platform that implements drag-and-drop. So we ship the models. We are using integers position in our intermediate table. We ship the business logic, and we ship our APIs. So now users can drag and drop the products, can insert, and other functionalities. But our key feature is drag and drop. User adoption, let's pretend that it's incredibly good. Every day, we have new users using our platform, trying our APIs. Everyone is happy. Engineers are very happy. Product managers are incredibly happy. Until one day. And here's the thing. When you have a problem in software engineering, there are two ways to know that the problem exists. First, and hopefully this is the most common one, you have a very good alerting system that notifies you when something is wrong. And second, and unfortunately this happens many, many times, I've seen it throughout my career, which is a human goes to the logs, talk to people, and see that something is wrong. So here's what we are going to do. We are going to look our DB write per minute. Imagine if every minute we read the logs from our database, we dump it into a data warehouse, and then we plot the following chart. This is database write over time. And there are two patterns here that looks very bad. First, we have spikes. And second, our DB write increased over time. This is not good. Database writes are not free. They take up a resource. Think about the following examples. Yesterday, we mentioned multi-tenancy. Imagine that one tenant write into the database too much, too often, in a very short period of time. Second example, imagine that you have a server or a service or an external client listening to our logs and processing the data. They're going to compute more and more data just because we increase the number of writes. Okay, we know that the DB writes increase and have spikes, but which table? So let's break it down. This is the same chart. The difference is that it's broken down by tables. And as you can see, there are a few tables that follows a flat pattern. But there is a single table that shows the spikes and the increase. This table is our newly released joint table. the one that holds the integer position to implement the drag and drop list. But which operation? Who is writing to this table? So let's look at the logs again. Let's break it down by all the operations that write to this particular table. And to our surprise, there are two operations that write the most: insert and reorder. And we have seen this before. This is the exact same problem as the books. Remember, have a very long list, insert at the beginning, relabeling all the books to the end. Okay, let's recap. Where are we now? We identify the problem. DB writes increased, and we have spikes. We look at our monitoring, and we notice that it was caused by reordering and inserting. Now, it's the time to go and explore a solution. So let's do that. If we go back to the basics, if we have two books, and they are too close together, it's physically impossible to insert anything in between. But there is an obvious solution in the real world. What if we leave a space between the books? Book A, space, book B. We can insert anything in between without affecting the books on the sides. Seems simple, right? But what happens when you run out of space? Let's define a new concept, a gap. If I have a book, a distance, and another book, that distance, let's call it gaps. And if a new book arrives and I want to insert it between the books, I have a couple of options. Insert it right in the middle, more on the right, or more on the left. But I don't really know where the next book is going to be inserted. So what I'm going to do is insert it right in the middle as my best guess. But if we do that, our gap between the left book and the next book is going to be shorter and shorter and shorter. Until one point where two books becomes too close together that I need to trigger a full rebalance. And by a full rebalance, I mean grabbing all the books and reordering them again with the same space between consecutive books. This has the exact same performance as inserting at the beginning and relabeling all the books to the end. The key difference is that we do this way, way less often. Let's define another concept, bisections. We can calculate exactly how many times we keep inserting in the middle until we need to trigger a full rebalance. Let's look at the following example. I have a distance of 10. If I insert in the middle, that's going to be 5. Insert in the middle, that's going to be 3, if we choose the ceiling. Again, 2. The formula is approximately logarithm base of 2 of the gap. Why I say approximately, this is because we cannot assume that the gap between each consecutive book is the same. We can have more gap at the beginning and less gap at the end. All right. Things so far has been very simple. And here is where I need your attention, because things are going to get trickier. If we remember the data type that we use integers in the intermediate table. And we use consecutive numbers, 1, 2, 3, all the way to the end. But between 1 and 2, there's nothing in between. We don't have the space. So our foundation is completely wrong. There are other great data types that works pretty well for this and follow the idea of spacing, book A, space, book B. We can use big integers, and we can have large numbers, non-consecutive numbers. 1,000, 2,000, insert in between, 1,500. We can use decimals. 1, 2, insert in the middle, 1.5. You might remember, working with decimals is hard at the application layer, divisions. Representation at the database layer sometimes is different than the representation at the application layer. But still, this is something that we can fix. We can work around it. And finally, there is a third data type that works pretty well. Strings. AA, AC, insert in between A, B. But which data type do we choose? The answer is all of them are valid. It depends on your application and the following factors that we are going to see in a bit. First, extremely important, storage size. How many bytes we are going to store for each element, for each list. For big integers, the size is fixed. It's 8 bytes for most of the databases. For decimal, same thing. The difference is that we need to define precision and scale. Precision is how many digits after the comma, and scale is before the comma. Strings, however, they are variable. The size depends on the number of elements, the number of characters that we have per each element. Second factor, remember, bisections, how many times we keep inserting in the middle until I need to trigger a full rebalance. The formula for this is the same across all data types. Logarithm base of 2 of the gap. Remember, approximately. Third data type, performance on reads and writes. We want our list to be very fast on reads and very, very fast on writes. This will depend on the data type that we choose. Most of the database love fixed storage size, integers comparing to 8 bytes versus 8 bytes. For strings, if you use long strings, we are going to make our database read and write slower. So we need to choose a very small list of elements. Finally, a very important factor, development cost. How much time does it take to migrate my list using my data type to the new data type? How many engineers and how many time? If you're already using big integers, but you're using consecutive numbers, the migration is only at the application layer. But if you want to migrate from integers to strings, the migration is a little bit harder. You might probably remember a data migration, and dealing with data migration is not easy, or almost never easy. So to summarize, all the data types are valid. It depends on your applications and the factors that we have seen. At Shopify, we chose strings, and we shipped several optimizations that I want to share with you. First, we use LexoRank for rebalancing. LexoRank was implemented by Atlassian for the Jira ticket system. The format is the first character is what we call the bucket. The bucket can be 0, 1, and 2. And the rest of the element is the string is the element. For example, here we have 0 as a bucket and then AAC, and AAC is the element in the list. When there is no room between the element, I have a couple of options. First is rebalanced, or the other is append a new character to the new element. See the following example. I have AA, AB, and I want to insert in the middle. I choose AA and N. N is the middle of the alphabet. The rebalancing is also done when there is no room and the strings are too long, or periodically, when the system load is low, and we can go and rebalance my list without affecting the users. Let's look at how buckets work here to visualize this problem. At any point in time, all my elements must have either the same bucket or a portion of the list has one bucket, and then the next portion has the following bucket. So 0, 1, 1 and 2, or 2 and 0. The migration consists in 3 steps. First, imagine that all my elements are in the same bucket, 0. I start migrating a portion of the list to bucket 1. I migrate them one by one or by batches, and then finally I migrate the remaining books to the new bucket. This might sound a little bit complicated, so let's visualize this with an example. For this, I'm not going to use strings. They are very hard to read. I'm going to use books, same as before. So here, two books are too close together, blue and yellow. All the elements are in bucket 0. So instead of locking the entire row and preventing users from writing, inserting, or reordering products, what I'm going to do is the bucket idea. And I'm going to migrate my right part of the list to my new bucket. In this case, purple, yellow, and blue are on bucket 1, but they are rebalanced. They have a gap between each consecutive book. And the left side, my red and green, they are not rebalanced, and they are still in the bucket 0. At this point in time, any user can insert or reorder without having to lock the entire row. And finally, I migrate the remaining of the books to the new bucket, bucket 1. And then again, from bucket 1 to bucket 2, and then from bucket 2, we migrate all of them to bucket 0. We also shipped several other optimizations. First, our initial element size is variable. We don't have the same element size for each list. Think about an example. Your music playlist. You probably have a playlist that is your top 50 songs, or your top songs, let's say. And I can assure that that list is very small. It has only a few elements. You might have another playlist that is all songs from the 90s. And we know that that playlist is going to have many elements. So when we create the list with only a few songs, we are going to allocate more characters to that list than your top list songs. The gap. We use an evenly distributed gap. This is, we look for usage patterns. Let's go back to the music playlist again. If you add a song to your playlist, you very, very likely add it to the first 20 items, or very rarely to the end of the list. So what we are going to do is leave more space at the beginning and optimize for the most common case and less space at the end. Finally, we ship several optimizations at the API layer. We ship an API layer that reads requests from the users and translates them into the simplest instructions to the database. Let's look at an example. I have 5 books, and the user is requesting us to move book number 2 and book number 3 to position 4. This is exactly the same as moving book 4 to position 2. The key difference here is that instead of doing 2 operations and 2 instructions to the database, I do a single one. This case might seem very simple, but let's scale this to millions of requests and millions of users every day, every hour. This is going to have a massive impact. Let's go back to our exercise. Remember, we shipped our drag and drop list. And now, this is one of the most satisfying charts in software engineering, when you ship something and this validates your hypothesis. In our case, we changed our data types, and our DB writes decreased, and we don't have spikes anymore. The problem is solved. So where are we now? We ship the incredibly good drag and drop list. We identify a problem, and we look at our monitoring and observed that that was caused by inserting and reordering. We explore, we prototype 3 different solutions, and we chose one. We ship it. We solve the problem, and then we measure the impact, and it had a massive success. But we are not done yet. And here is where most of the developers stop working on the project, and that's wrong. There are still 2 key steps that are missing here. Remember, we found the problem, we fixed it, but still there are 2 key steps that we are missing. I'm going to give you 10 seconds to think about it. We need to prevent any other team or developer from having the same failure, increasing our database write and having spikes. And that's very easy to reintroduce if you didn't have this context. And we can do that very easily. We can add monitoring to our logs that listens to all the DB writes and look for any anomaly at the database layer. Could be spikes, could be increase, or could be decreases if we have downtime. This 6-step framework works very well for any performance problem that you might have. Of course, the hard part most of the time is finding the solution. Others is implementation, and the solution is obvious. But still, this applies very well. And finally, this is optional, but I really like this step, which is do things, tell people. Share to the world what you have learned. Share the numbers. It could be humans, or it could be a blog post, and an LLM can read it. We are reaching the end of the talk. And I want to share with you a few takeaways. A very simple problem, reordering items. It's very simple, but it's very tough at scale. Using integers is completely fine if you have a small list, but it does not scale. We solved the problem together. We saw a framework, 6 steps, that works very well for any performance problem that you might have. And finally, I'm coming back to the beginning of the talk. Now, if you ask AI to implement a drag and drop list, you will know the answer. Thank you.